Eh, Buenas tardes a todos. Mi nombre es María Florencia Segovia y como presidente del capítulo profesional de la Colombia, es un placer para mí darles la bienvenida a este webinar, el último evento virtual que vamos a tener este año, con una temática tan importante como la geotermia. Bueno, aprovecho además para invitarlos a que nos sigan en redes, Instagram, LinkedIn, WhatsApp, que se sumen a nuestros grupos, nos sigan, ya que ahí compartimos información sobre los eventos que vamos organizando, más adelante los cursos que vamos a ir dictando. Y también los invito a que se sumen, se afilien. Si querés, por favor, Luis, dale next, siguiente. Gracias. Se sumen a nuestro grupo, un grupo muy lindo, donde pueden compartir sus conocimientos, sus experiencias, pueden participar también de sesiones como estas o de cursos. Y también a que se afilien, por favor, siguiente, Luis. A partir de la página web se pueden sumar, pueden afiliar como miembros de forma gratuita o si no, pagando un fee de $40 para las personas que estén acá formando parte de los capítulos de Latinoamérica. Bueno, no quiero quitarle más tiempo a la sesión de hoy. Les agradezco nuevamente que estén aquí presentes. Muchas gracias por su participación. Espero que los disfruten y bueno, muchas gracias, Tom. Damos inicio entonces, Ulises, a la sesión. El auditorio es todo tuyo.
Muchas gracias, María Florencia. Buenas tardes a todos. Muchas gracias por esta participación. Vamos a tener hoy el agrado de tener a Tom Bradley con nosotros, compartiendo el tema Application of Gas and Oil Subsurface Evaluation Methodology to Geothermal, the Value of the Data. Tom Bradley is a senior petrophysicist advisor with Baker Hughes, specialist in open hole formation evaluation. After graduating from the Royal School of Mine, Imperial College, London, with a degree in geology with engineering geology in 1996, Tom started his career in 1997 with Western Atlas International, and since then, Tom has worked in a variety of technical and supervisory roles in a variety of countries. Tom is currently based in the Netherlands, and as part of his current role, he's involved with the development of geothermal energy in the Netherlands and Europe. So, Tom, it's all yours. Thank you. You are mute. Yeah.
I'm still getting the hang of Teams, so thank you very much, Ulysses. Thank you very much, Maria Florencia. Let's try this again. So just checking, can you see the screen?
Yes, we can see the screen, Tom.
Perfect.
Thank you.
So I'll say thank you very much for the introduction, and I'll say welcome to my talk, everybody, the application of oil and gas subsurface evaluation methodology to geothermal, the value of data. And as mentioned, I am Tom Bradley with Baker Hughes in the Netherlands. So with my presentations, I always like to start off with a question. So as we know, we are the Society of Petrophysicists and Well Log Analysts. Why should we as a society care about geothermal? And quite often, when you think of sort of like new energy, alternative energy, you sort of think of your, say, environmental protesters, some pictures here of presenters in Scotland, well, protesters in Scotland, don't frack, all this sort of thing. So why should we as a society care about geothermal? And I think the reason is this. Because as we know, sort of the world is changing. And you may be aware of the Paris Climate Agreement that was signed in 2016 and also ratified at the meeting in Glasgow the other year. And that agreement, 195 countries ratified that agreement. And at this meeting, what they agreed to do is they agreed to restrict global temperature rise to less than 2 degrees Celsius above pre-industrial levels. So what implications does that have? I mean, one in particular, it's going to imply it's going to need a significant reduction in carbon production. And therefore, that also implies a reduction in hydrocarbon use. And of course, if this means reduction in hydrocarbon use, that energy is going to have to be replaced. So it's going to have to be replaced from somewhere. And what's the obvious place to replace that? It's obviously renewables. I mean, renewables we're all familiar with. For example, wind, hydroelectric, solar, biomass. Say whether biomass is a renewable depends on your, say, point of view, but I'm including it here. And also another potential renewable is geothermal energy. So it could all be part of this new energy mix. So the next thing, geothermal energy. I guess some of you in the meeting will be familiar with geothermal. Some of you not so familiar with geothermal. What I'd like to do, just start off with a quick description of what geothermal energy is. And I have this description here courtesy of the EIA in the United States. So I'm going to read this. So geothermal energy is heat within the earth. Say the word geothermal comes from the Greek words geo, which of course means earth, and therm, which of course means heat. And say geothermal energy is a renewable energy source because heat is continuously produced inside the earth. Say people use geothermal heat for bathing, to heat buildings, generate electricity, and other uses as well. And you'll be pleased to hear this is the only slide I'm going to read. Because what I'd like to talk about next is, say, describe what geothermal energy is. You may be wondering what you can use it for. And the thing about geothermal energy, it's got a whole range of uses. And we're going to start here, sort of some various descriptions of what you can use geothermal energy for, starting from shallowest to deepest, sort of coolest to hottest. And what we have at the coolest is, say, domestic and sort of small-scale heat pump installations. And what these are sort of like a borehole or a trench, sort of less than 150 meters in depth. You're looking at subsurface temperatures up to about 40 degrees Celsius. And where this is used, it's like small-scale domestic heating and cooling. And where this can be applied, this can be basically applied worldwide. And in fact, on a personal level, I was actually looking at installing one of these in my house here in the Netherlands a few months ago. Unfortunately, the economics didn't work out because I'm living in an already built house. But what you're finding in many places in the world now is new build houses. These are being installed because it's actually sort of worthwhile, both economically and in terms of energy production, doing this. So then we go a bit deeper. Then we have what we call low temperature geothermal. And by sort of depths here, I'm talking about less than 2,500 meters TVD, temperatures between about 40 and 100 degrees Celsius. And the application of this is things like district heating and agriculture. In fact, I've actually got two examples here in these pictures here. Say where it's supplied, Netherlands, France and Germany. So this picture here is actually a district heating installation in The Hague, here in the Netherlands. So you go past this on the tram, you wouldn't even know what it is. But this is heating several thousand houses in The Hague. And here's an example, sort of greenhouses. So to be here in the Netherlands, where I'm based, is geothermal energy actually got started off by the farmers. They were looking to reduce their energy costs because they're heating their greenhouses with gas. And these farmers basically tried a geothermal well about sort of 15 years ago, and it worked. And of course, farmers being farmers, their neighbours found out because we're saving a lot of money, and it just spread. And some of you might not be aware of this, but sort of in France, Paris, sort of suburbs of Paris, some of these suburbs have been heated by geothermal energy since the late 1970s, early 1980s. And Germany's a good example, city of Munich. Sort of the city of Munich has got about 7 or 8 geothermal wells now, heating a significant part of the city. So that's sort of low temperature, sort of depth to about 2,500 meters. Then we go a bit deeper to what I'm terming here as mid-temperature, and sort of depths of about less than about 4,000 meters, and temperatures between about 100 to 150 degrees Celsius. And the question is, what's this used for? This is, for example, industrial uses, things like food processing, industrial drying, so on and so forth. So big users of this, countries like East Africa and New Zealand, sort of used for fish farming, things like this. And then we go to what we call high temperature geothermal. And these are depths, say 4,000 meters or greater, and temperatures greater than 150 degrees Celsius. And this is commonly sort of the geothermal that people think of when you see geothermal. Sort of an example by this picture here, which is a geothermal power plant in Iceland with steam coming out of the ground. Say, what's the use of these sort of temperatures? Power generation. And where do you find this? I mean, obviously, Iceland is the poster child for this. Everybody knows about geothermal in Iceland. But many people are surprised to hear California is very big on this, sort of San Andreas fault, seismically and volcanically active, a big producer of geothermal power, electricity. And also Turkey, sort of located on two plate boundaries. Turkey is a hotbed, if you excuse the pun, of sort of geothermal power production, electricity production. So some examples here of what you can use geothermal energy for. A wide range of uses, from heating, anywhere where heat's sort of required, basically. So that's a little bit about what is geothermal energy, sort of geothermal uses. Now I'd like to talk a little bit about geothermal systems. I mean, of course, to have geothermal energy, you need to produce this power or get this heat from the subsurface. And really, you can sort of break geothermal systems down into sort of 3 or 4 systems. We start off with what we call direct use, sort of signified by sort of this part here, where you have a well, you drill down into the subsurface, into rocks that are hot enough, and basically just extract the fluids, the hot water from the subsurface, and use it for whatever use you want to use. However, that doesn't work everywhere. What you more commonly find is what you call these hydrothermal and enhanced systems. And the way these work, these use what's called a doublet, as demonstrated by these parts of the little diagram here, or courtesy of the US Department of Energy, by the way. And the way this works, you have 2 wells. You have one well where you pump cold water down, then put very simply, this flows through the formation, either the natural porosity permeability that's present, or maybe you have to sort of stimulate the reservoir, create fractures, create sort of a permeability pathway between the 2 wells. As it goes through the formation, heats up, comes out hot. So then you have the water produced. You pass this through a heat exchanger to extract the heat from your formation fluids into your working fluid. Then you use sort of this working fluid for whatever you need to do, say district heating, power production, so on and so forth. Now, the third system, which is sort of becoming a sort of a talking point more recently, is what's called closed loop systems. Say some of you may have heard of a company called EVA, who sort of pioneered the technology in Canada, now doing sort of a proof of concept project in Germany. The way this works is they actually drill multiple well bores into the subsurface and connect these well bores in the subsurface to each other. And then use these subsurface well bores as a giant heat exchanger, a giant reservoir. So no fluids actually flow through the formation. The fluids are completely restricted to the well bores, just extracting the heat from the formation this way. So these are sort of the common systems you come across. Direct use, hydrothermal enhanced, where you use a doublet, and the closed loop, where you flow the working fluid through the wellbore, not through the formation. So that's a little bit on the various sorts of geothermal systems. But what I'd like to talk about next is how does geothermal energy sort of compare to some of the more established sort of renewables like wind, solar, hydro, and so on and so forth. Now, one benefit of geothermal is it's potentially available everywhere, because as we all know, you drill down into the earth, it gets hotter. So in theory, you just need to keep drilling until you get a temperature that meets your needs. So you can have this pretty much anywhere, in theory. Another advantage is sort of geothermal is it's got very little reliance on sort of variable environmental factors. So it can provide a constant baseload. The example being, compared to solar. Does solar work at night? No, because it's dark. Compare it to wind. Does wind work when it's not windy? No. However, the earth is always hot. So potentially geothermal energy is completely unaffected by variable environmental factors. So can provide a consistent baseload. Another advantage of geothermal, practically zero emissions once the wells are realised. And also a small footprint. I mean, I refer to the slide I showed previously, that project in The Hague. The actual building is the size of perhaps a church. If you're going past it, you wouldn't even realise it. So once the rig has gone, the actual footprint of the installation is tiny. And also sort of the life of the projects, sort of if the subsurface is correctly managed, these projects, the geothermal energy installation, can have a project life or installed life of 30 years or more. Sort of a long life, much longer than a wind turbine or solar panels. So they're the benefits. But of course, as with all things, there's some downsides. So the downsides of geothermal at the moment. At present, currently, it's very capital intensive. As we all know, drilling wells is expensive. As you can imagine, selling hot water, you won't get the same money back as you will selling oil and gas. So quite often, the economics of a geothermal project can be somewhat challenging. Another one is a lack of public understanding. Say, compared to sort of solar, wind, they've been around a long time, sort of the wider public understand them, they accept it. However, geothermal energy is new. And sort of here in Europe, for example, you pop up with a drilling rig in somebody's back garden. What are they going to think? Maybe fracking, which is not popular here at all. So there's a lack of public understanding and sort of the lack of social acceptance at present because the general public maybe don't understand it so well, the unfamiliarity. Another potential sort of drawback with geothermal is the potential environmental effects. Of course, as we know, we're pumping water into the subsurface, changing subsurface pressure. What can this result in? Perhaps reactivation of faults and fractures, and maybe detectable seismicity at surface. Here in Europe, there's been some big problems with seismicity. Sort of one place that's well known is the Basel project in Switzerland, maybe 15 years ago, closed down after 3 months because of detectable seismicity. Currently in Strasbourg in France, they're having some seismicity problems from the geothermal projects. And also here in the Netherlands, some of the early projects have had some seismicity issues associated with them. So potential environmental effects such as seismicity can potentially kill a project. Another big sort of potential problem is a lack of required infrastructure. As you can probably understand, say district heating from geothermal, you can't transfer the heat very far. So you need to have your geothermal project, say for heating, where that heat is used. Therefore, you need a district heating grid. Maybe that heating grid doesn't exist. Equally, let's sort of talk about power production. Of course, you need a connection to your sort of electricity grid for your geothermal power plant. Maybe that is not near your most ideal geothermal location. Another sort of potential drawback is geothermal as an industry. I'm saying it's young here, but in reality, it's been around since Roman times. I'll take sort of the example of Bath, where they were sort of producing geothermal heat for bathing. But in terms of large-scale geothermal, it's quite young. So therefore, compared to other renewables, there's less expertise there yet to realise projects, and still quite a lot to learn. So there's some of the pros and the cons. What you're probably also wondering is sort of, how does geothermal sort of figure in the entire sort of renewable energy mix, sort of the global installed capacity? So what I've got here is some numbers where we're comparing different, well, sort of 5 different sorts of sort of renewable energy. We've got hydropower, wind, solar, biomass, and also geothermal. And here's sort of the global installed capacity in gigawatts from 2016 to 2020. And also a slide here showing sort of the added capacity in 2020. And what you can see is that the installed capacity of renewables is increasing. But you're probably looking at this graph and thinking, where's the geothermal? And when you look very closely, it's that very thin sliver at the top. So compared to other renewables, the actual installed capacity of geothermal is very, very small. But let's zoom in on that. And here's some more numbers I found, say, awesome by Statista, by the way, of sort of the growth in geothermal from 2009 to 2020. And what you can see, over that time, it's increased by 50%. And the trend is only growing. And of course, think of sort of the current situation in the world, current global sort of political situation, gas supplies. Geothermal's ideal for heat. Of course, gas is mainly used for heat. So going forward, here in Europe, I can see this installed capacity growing further and further. So what can we take away from this slide? I think it's this. So at the moment, geothermal, the installed capacity is quite small, but it's growing and also growing rapidly. So I think there's a bright future for geothermal. So you might be wondering, okay, this is the installed capacity. Where's it installed? So I show this graph, sort of this is from a couple of years ago, what the current installed global capacity for geothermal is. And quite often, I'll say in these presentations, where do you think the largest installed capacity for geothermal is? And many people think straight away, oh, it's going to be Iceland because of the pitch of the steam coming out of the ground, so on and so forth. People are quite surprised when they see the actual largest user of geothermal energy is the United States, which is almost double the next sort of participant, which is Indonesia. And you look at these lists, it's of course quite often Pacific Ring of Fire countries, Indonesia, Philippines, New Zealand. You've got areas sort of associated with volcanicity, sort of Mexico, Italy, Kenya, for example, Iceland, of course, Japan. And then there's the others. So surprisingly, the United States is the biggest user at the moment, with sort of typical expected countries following this. So that's a little bit about geothermal. So what it is, how it works, where it's installed, and what you can use it for. What I'd like to look at next is the economics. Sort of, how does the cost stack up? How does sort of the economics stack up? So I'll show you this graph. And of course, this is a graph I'm sure many of you are familiar with, of course, from oil and gas. The actual sort of risk cost return as shown by this graph in terms of your risk on this graph, your time here, various stages of exploration, realization of the project, and your cumulative cost by this line here. And you'll see it looks very, very similar to what we're all used to from oil and gas projects. Say we start off with an initial exploration stage where the risks are pretty high. But at the moment, you're looking at, say, desk studies, researching literature, widely available data. The actual costs are quite low. Of course, you do your exploration, you identify a potential site. Then you start drilling and looking at feasibilities. And of course, when you start drilling, you found a potential target, your risk's going to decrease considerably. However, your costs are also going to increase considerably. So now we've got to the stage we've found a potential location, area for a project. Then you start developing. As we all know, once you start developing projects, the costs increase exponentially, significantly. Your risk is reducing when you're putting in infrastructure, sort of getting better knowledge of your reservoir, but your costs are increasing significantly. And of course, it's worth mentioning, all throughout this stage, is any money coming in? No, it's not. You're just spending money. And of course, it can be a significant amount of money, sort of tens of millions of dollars, perhaps, and you've got no return coming in. We all know how long these stages take. Typical geothermal project, maybe 2 to 4 years. So then you get to the stage eventually, of course, where your project is in place, you're starting to produce energy, you're selling your heat. So now your costs start to level off. And now this is a stage that could be 20 years. So now you're selling your heat, you're getting the return on your investment. So your long operating phase, low cost, and hopefully steady returns. So now you're sort of paying back your investment. The question we have, as we know, you're not going to get as much money selling hot water as you're going to get selling oil and gas. So how can we sort of reduce the time and costs of this part of it, where you're realizing your project, and how can you lengthen this part of the project, where you're selling your heat, getting your economic returns? So talking about costs, you may be wondering, how does sort of geothermal energy, let's say the cost per kilowatt hour, stack up compared to other energy sources? So what I've got here is some examples, geothermal with some other sort of renewables and non-renewable energy sources, sort of solar photovoltaic, solar thermal towers, geothermal, of course, wind, gas, nuclear, coal, and gas combined cycle. And what I can see, and unfortunately I've got no numbers on this axis here, I actually didn't put them on the slide, but overall, once it's installed, geothermal is actually pretty competitive with other energy sources. Of course, this comes with a but. As we all know, the risks in geothermal are higher than other sources of energy. For example, let's think about wind. You know, even before putting your turbines in, if it's going to be windy or not. You know, if you're going to put solar panels up, you know it's sunny. But when drilling a geothermal well, do you know how hot these rocks are going to be? Are there going to be sufficient heat energy in the ground before you drill that well? You don't. So your risks are much higher. And of course, we all know drilling wells is expensive. I said it before. You don't get as much money selling hot water as you do selling oil and gas. So the actual return on this investment can be a lot longer than some of the other renewables. As we all know, wind turbines cost a lot of money, but they're quick to put up, and you've been guaranteed a return pretty much straight away. So again, how can we use subsurface knowledge to sort of reduce these risks associated with geothermal and improve our returns? So that's a bit of a background on the economics. But now I'm going to talk about how does geothermal energy, especially the subsurface side, compare to what we all know, oil and gas. And the first thing I like to say is I actually think that the geothermal industry and the oil and gas industry have got very, very similar objectives, which I'm going to say is this. So the safe economic extraction of a subsurface energy source with the minimum of adverse effects on the environment, which I think is actually a fair statement for both the geothermal industry and the oil and gas industry, safely producing a subsurface energy resource. So the question is, how do these two industries compare? I'm going to start with oil and gas, which is what we all know, of course. So what do we know about the oil and gas industry? I mean, the first thing is it's an established worldwide industry. It's been around a long time, over 150 years since the first wells were drilled. And of course, in that time, a wide variety of companies have sort of built up. You've got everything from your super majors, your national oil companies, your Exxon Mobils, your Aramcos, your Shells, so on and so forth, all the way down to your small independents and everything in between. And of course, because the industry's built up, it's also developed a well-established service industry to support it. Same with Self and Baker Hughes, and of course, the other service companies we're all familiar with. And of course, over that year, over 150 years, we've built up a lot of experience. So we've got the methodologies to drill wells, we've got the best practices, the legal frameworks there, the regulations are there, and also all the safety side, so it can actually safely and economically utilize these resources. So let's compare that to geothermal. So how does geothermal compare? Now, geothermal as an energy source has been around a long time. For example, the Romans and Greeks were using it sort of 2,000, 3,000 years ago. It's also been around globally, but as sort of a major industry, it's only really been growing in the last few years. So it's very few major operators and is still small compared to oil and gas. And of course, because it's a small industry, there's, as I say, very few major operators. I could probably name them on the fingers of one hand. And the supporting industry hasn't built up. You haven't got the service industry developed to support these major players. Of course, it's fairly young, fairly sort of recent growth. The knowledge is still building. The knowledge base is growing, but it's still gaps. Sort of how do we best sort of utilize the subsurface? Maybe the legal framework's not there yet. Sort of still learning on HSE. And because of this, being a relatively young sort of in terms of development industry, haven't got the best practices. Sort of methodologies haven't been developed of how we can actually sort of safely and economically utilize these resources. So I think that leads to the question, is how can the oil and gas industry contribute to the future and success of geothermal? What I'd like to say first is let's look at oil and gas. Say, what's important for the oil and gas industry? What do we need to know? And of course, I'm sure you're all shouting at the screen now, what's important for oil and gas? I like to say 4 things, really. Where are the hydrocarbons? How much is there? Is it going to produce? And what's it going to cost? So the question is, what controls all this? I think it's really 5 things if you sort of distill it down. Sort of your reservoir structure, thickness and aerial extent. Where are the hydrocarbons? How much is there? Your porosity and hydrocarbon saturation. Are they going to produce? Your permeability. Or also how it's going to produce, your recovery factor. And of course, what's it going to cost? We know how it's going to cost to extract. You can work out the value of the hydrocarbons in place. Therefore, you can work out if a project is economic. So that's oil and gas. Let's compare that to geothermal. And I'm sure all you guys and girls on the call I said, what do you think is important for geothermal? You'd probably start screaming at the screen, well, temperature's obviously going to be important, isn't it? Because, well, I'll tell you in a minute. Maybe permeability is important. Maybe your effective porosity is important. Also, maybe the presence of fractures is important. So the question is, what do we want from these properties? Do you want high or low? Generally, with all these, higher is better. And the question is why? Excuse me. Temperature is probably the obvious one. The hotter it is, the more heat you're going to produce. Why is permeability important? What you'll hear very often in the geothermal industry is that flow is everything. Of course, you have better permeability. You've got more flow. And of course, you've got more hot water coming out of the formations. You're going to be producing more heat. How about porosity? Is porosity important? It may well be, because let's think about this. You have a high porosity formation. You're going to have more surface area to actually transfer the heat from the formation to your working fluid. How about fractures? Why perhaps do we want more fractures? Because in some ways, fractures give you the benefit of increased permeability and increased effective porosity. You've got more surface area to transfer the heat. As we all know, open fractures are generally pretty permeable. You're going to get that fluid out faster, so better heat production. But the question is that everything? Is there more? Maybe are things like lithology and geochemistry important? Are perhaps your formation water properties important? Maybe your formation reservoir structure is important. And how about your geomechanical properties? Is that important? The question is why? Because let's think about lithology and geochemistry. Think about the example of a doublet-based system, where injecting water into the formation, flowing through the formation and producing it. Let's think about this. How is this going to affect our geochemistry? Maybe different lithologies are going to react differently to the water. Maybe you've got dissolved salts in your water. And of course, could this perhaps lead to sort of pore plugging or adverse geochemical reactions in the formation that will reduce your flow? Another one is formation water. As you say, formation water, we all know formation water is salty. And of course, we're producing hot, salty water, taking it to surface. What's going to happen as you take it to surface? It cools down. What's going to happen to the salt in that water as it cools down? It'll precipitate. Perhaps it will plug your pipework. And also, as we all know, hot, salty water is corrosive. What's it going to do to steel casing? It's going to dissolve it. Mentioned already, produce scale. We all know some scales are radioactive. So, of course, you've got radioactive salts deposited in your surface facilities, an extra HSE consideration when you sort of decide what to do with it. How about your formation reservoir structure? The question is your well in the optimal position? Because, of course, you think you put in a better reservoir, you have better flow, higher temperatures, more heat produced. And equally, on a doublet-based system, you've got two wells, one injecting, one producing. Is your water going where you think it is? What happens if your next door neighbour drills a well over there and the water's actually flowing across here? You have all the costs. He has all the benefits because the water's flowing into his well. Equally, your geomechanical properties, things like your rock strength, fracture strength, your changing subsurface pressures. Are you going to reactivate faults, have seismicity? Equally, you're going to have things like perhaps compaction affecting your wells, and also wellbore stability. Once you start drilling your well, could you potentially lose it because the geomechanics aren't conducive to drilling in a certain direction? So all these things to think about. And it's even more. As I said, geothermal industry on a large scale is fairly young. So what don't we know? And what we've got to learn? So now, talk about what we actually do in a geothermal well. What's commonly done nowadays? How well do we actually know the surface? And a good question is, at the moment, what is commonly recorded in a geothermal well? And what you often find in terms of subsurface acquisition, in terms of logging, WIRE and LWD, at the moment, many operators, because the economics are quite challenging on these wells, see logging as expensive. So therefore, it's often limited. You may only have a gamma ray, just sort of shale or sand. Sometimes you might get resistivity, maybe join your LWD, just to find your formation tops for stopping. So you find a sand body, great, we're in a permeable porous sand, we'll stop. That's where we put the well. We said already, ideally you want to know things like porosity, permeability, or thermal properties. So where do we get these? Quite often, this is inferred from other data. It's not measured directly. As I said earlier, in a geothermal well, flow is everything. So how do we determine our flow? Quite often, a well test will be conducted, because many of these wells are actually dependent on subsidies from sort of governments to be economic. And sort of the subsidy is dependent on the well flowing. So many of these operators will perform a well test. As you all know, a well test, it gives you a bulk measurement of flow. But does it necessarily say where that flow is coming from? And the answer is no. So what's the implications of this? Actually, it's quite a high local uncertainty on your formation properties. So I'm going to go back to where do we get this data from? And as I mentioned, quite often, public data is a very good source of information for these wells. As we know, many countries have sort of very comprehensive subsurface data repositories. And I'm going to refer to the example here of the Dutch one, which I'm very familiar with, the Dutch NLOG subsurface database. So what this is, here in the Netherlands, we're actually very fortunate because 5 years after acquisition, all data goes in the public domain. Oh, has my connection just dropped? Just to confirm, can you all still hear me? I think I might have lost the connection.
Yes, Tom, we can hear you and we see your slides.
Excellent, because one of my screens has vanished. That's good. So I'm going back to the example of the Netherlands and say we're lucky here that sort of the Dutch NLOG database, everything older than 5 years goes in the public domain. And you can see it's very comprehensive. What I've got here is a screenshot, and all these dots represent wells drilled in the Netherlands. What I'm going to do now is zoom in onto the land-based wells. So here's the wells on land, because at the moment it's worth mentioning geothermal is only done on land, because no point doing it offshore. too far away to get the energy to the land, and also not economic. It's all land wells. So here I've got plotted all the wells on land in the Netherlands. What I'm going to do now, I'm adding the geothermal license areas. And what you'll see is in many areas, sort of often these geothermal license areas are areas of population centres. For example, one here near Amsterdam, one here near Utrecht, several around near Rotterdam, some over here, sort of Eindhoven area, Groningen, sort of down near Maastricht, these areas. And what you often see, many of these areas don't have any wells, because quite often these wells are, or maybe just a handful of wells, maybe drilled in the 1940s, 1950s, didn't find any oil or gas, so therefore are they going to drill any more wells? Even some examples around here, sort of this area down here. Looks like it's loads of wells. What it doesn't tell you, all these wells were drilled in the 1900s for coal exploration. No log data, only go down a couple of hundred meters. So in terms of subsurface data for geothermal, 2,500 meters, no use. So this is just the example of the Netherlands. What you find is many other countries face very similar challenges. All the potential areas for geothermal have very little data. So now to show the value of even limited data for geothermal, I'm going to present a case study of a project I worked on a few years ago. And the background of this case study is this: sort of what are the implications of having limited subsurface knowledge, and how can even limited data tell you something? This case study, what this was, it's a well somewhere near here, I can't say exactly where, but it was a sort of a fractured geothermal well, potential prospect, where there's 113 meters of open hole interval. And what was assumed was that the majority of the interval would flow. Fortunately, the actual operator ran some logs, and these are presented here. Say they ran nuclear magnetic resonance logs and borehole acoustic logs. And this is the data presented here. Say I'll talk for those who are not familiar with the data. First track is gamma ray, as many of us know. Low gamma rays, clean formation, your carbonate. Higher gamma rays, shale, sort of not potential formation. And here it's all low gamma ray, so looks pretty clean. The next track I'm looking at here is the nuclear magnetic resonance data. So for those who are not familiar with NMR data, the easy way to read it is this. You can see a series of peaks here. And these peaks, the position of these peaks from left to right, basically represent your pore size, with small pores being represented by peaks on the left, large pores being represented by peaks on the right. And the assumption is the larger the pore, the more likely it is to flow. Of course, by looking at your distribution of pore sizes, if you have a lot of large pores, very few small pores, you can make the inference, large pore throats, good permeability. And that's represented by this track here, this yellow shading. As you can see here, we have areas of large pores, lots of permeability, areas of small pores, low permeability. And then you can look relates to your movable porosity, the yellow shading here, representing porosity that can potentially move. So what we can see here is we've sort of got permeabilities up to about 200 millidarcies, porosities to about 15%. So if we do a quick net to gross on this, what you see, just some arbitrary cutoffs of say a minimum movable porosity of 5%, permeability of 2 millidarcies, do a quick net to gross, we've got a productive interval, 36 meters. So I've gone from assumed 113 meters to 36 meters. Not looking so good now, is it? But then this operator did a well test. I did some production logs and they ran some spinners to actually see where the flow was coming from. And what they found, for those who are familiar looking at production logs, the key curves to look at are these curves here. And these are the spinners. When you see a change in the spinner, this indicates flow coming into the well. And also this curve here, differential temperature, you see perturbations in the differential temperature curve. This tells you where your flow is happening. When we look at this, we can see flow over 1 meter, one interval. So I've gone from like 113 meters of flow, potential hoped sort of reservoir or hoped productive interval, down to 1 meter. And the question is why? What's going on here? So fortunately as well, this operator decided to acquire some data. It was limited, just nuclear magnetic resonance, full waveform acoustics. But even look at this limited data, it can tell you something. This is what I've got plotted here. So I have the curves I showed before with your production log data. We've also got the waveform data from the acoustics, so the dipole waveforms. And what you'll see, this interval we have flow, your waveform is getting significantly attenuated. And one of the other approaches we can do sort of full waveform acoustic data, you can do what's called near borehole reflection imaging. And some of you might not be familiar with this, but the way it works, very similar to sort of seismic, but turned on its side. It's sort of demonstrated by this little cartoon here. You've got your borehole, you have your acoustic tool in the well with your acoustic transmitter, acoustic receivers. And with sort of specialist filtering, you can sort of treat this almost like surface seismic data turned on its side. So you have like sort of reflecting plane in the formation. It's got an acoustic impedance contrast. This waveform data actually reflect off it, and you can record these reflections. Then by applying some interpretation methodology, you can generate an image like this. This represents sort of the near wellbore structure, sort of just around the wellbore, with the wellbore plotted in the middle. And we're looking 25 meters either side of the wellbore. And same here, I'm showing this on screen, say, it doesn't look much, but I'm sure you're all sitting maybe in sort of at home in your office, and maybe your office is 2 or 3 meters across. Say, multiply that by about 8. And that's how far either side of the wellbore we're looking. And what you can see straight away, looking at this, you can see sort of this feature here, like a planar linear reflective feature. And if you sort of then sort of project this to the wellbore, it intersects a wellbore here and project it across, and it's intersecting exactly the interval, the depth, where all the significant flow is coming into the wellbore. So I can look at this and say, okay, all our flow here is potentially being caused by one significant open fracture. This is the only sort of part of the wellbore contributing to flow. So knowing this now, what are the implications of our improved subsurface knowledge? Or even if we didn't know this, how could this affect a project? And the first thing is, perhaps you'll have poorer performance than expected. You sort of made some assumptions about your well, turned out when you drilled it, it wasn't as good as you hoped. So poor performance. And of course, with poor performance, what may be going to come with that? A lower economic return. So it doesn't make as much money. Therefore, it's not going to be as attractive to your investors. Let's look at some other things. Let's say you didn't have the geochemical knowledge and you started producing the well, producing the geothermal fluids, and you had scaling and corrosion problems. Of course, these are going to cost money to rectify. Let's say you had unexpected solid productions. It's worth mentioning many of these geothermal wells are dependent on ESPs, electrical submersible pumps, to actually produce the fluids, because the subsurface pressure isn't sufficient to flow sufficient volumes on its own. So you need pumps. And of course, you've got solids being produced. You don't know your geomechanics so well. Pumps don't like solids. It tends to wear them out and break them. And some of you know, ESPs are expensive, both in terms of the pump itself and the cost to replace them. So your pump wear, again, affects your economics. Look at the example here, you have a fault. Let's say your subsurface drawdown is too high, you reactivate that fault. Core seismicity, with of course the obvious negative implications. And also, what else? What else don't we know? What else could sort of come around and bite us later in the life of the project? Maybe we don't know. So the question is, how can sort of subsurface knowledge benefit geothermal? In this case, economically. So here I like to do a thought experiment. And the way we do this, here in the Netherlands, sort of for any geothermal operator, they have to use this Dutch government-provided program called DubletCalc, which takes some subsurface properties, porosity, permeability, aquifer thickness, some other properties. They plug this into this software, and it works out your potential energy production. So what I've taken here is like the base standard case in DubletCalc, which has a net to gross of 0.8, and you run the numbers, it produces 8.33 megawatts of energy. That's a prediction. So I can do a thought experiment. Let's say we took our geothermal well, we actually steered it to improve our net to gross by 5%. We go from 0.8 to 0.85. What potential implication could that have on our energy production? We take the example, say, of a sand shale well. I'm sure many of you are familiar with steering wells using, say, your porosity logs, deep azimuthal resistivity, density, nuclear magnetic resonance, so on and so forth. And we just keep the well in the most productive, so the most porous permeable zone to increase our flow. As I said earlier, flow is everything, to improve your net to gross. So just by increasing our net to gross by 5%, how is that going to affect the economics of a project? We can look like this. So we started off with 8.33 megawatts at 0.8 net to gross. We go to 0.85. takes us to 8.77 megawatts, which is 440 kilowatts. So how do you visualize 440 kilowatts? It turns out that 440 kilowatts is the power output of a Tesla Model S. So what's that worth in economic terms? So a little bit of a sort of back of an envelope sort of thought experiment calculation. Let's say wholesale electricity price is 0.1 euro, so 10 euro cents per kilowatt hour. It's actually higher now. This works out over the course of a year, it's 400,000 euros of extra revenue. So I think that's not a number to be sniffed at. Of course, you can imagine you're increasing your net to gross. You're probably increasing your permeability as well. So what happens if we increase our permeability by 5%? So we go from 250 millidarcies to 263 millidarcies. This takes us from our previous base case of 8.33 megawatts to 9.07 megawatts. Again, your back of an envelope calculation, that works out to 650,000 euros extra revenue a year. I mean, the project life is sort of 20 years, perhaps. 20 times 650,000 euros is a lot of money, which is easily going to pay for sort of the acquisition of some subsurface data to sort of better know your reservoirs, your geothermal prospect, and make better use of it. So now to conclude, so what I've hopefully shown is that geothermal as an energy source is viable. It's a viable, economically friendly, environmentally friendly energy source. But at the moment, unfortunately, sort of the application of subsurface evaluation to geothermal is often limited. But fortunately, since I started presenting this presentation, I've seen the mindset turning around. And operators are now getting that information to better utilize their resources and improve their economics. So what I've hopefully shown is the overlap between geothermal and oil and gas. It's too good to be true. It's perfect, because all the evaluation principles we apply in oil and gas, they're all equally applicable to geothermals, because geothermal operators need to know the same things. However, I mentioned already, things are changing, but subsurface data up until recently was sort of seen as an unnecessary expense that should be minimized. But even though people are now starting to realize that sort of direct measurement of some of these key properties, porosity, permeability, would be very beneficial. And also some other things, sort of lithology, geochemical properties, geomechanical properties, so on and so forth. Because sort of in the immediate time, the benefit may not be obvious, but sort of the need for them may only become apparent many years in the future. I can give you an example here in the Netherlands of some of the very early geothermal wells were drilled with and sort of complete with steel casing. People didn't think salty water, 10 years down the line, they're all dissolving, big corrosion problems. Sort of knowing that geothermal, well, this water properties earlier may have solved some of these problems or mitigated it and saved potentially a lot of money. And of course, when you need to know this data, it may be later in the life of the well. Your rig's gone, your completions are in place, your pumps in the well. So it may be impractical or even impossible to get this data. And of course, very expensive. But knowing this data, of course, it gives you the possibility to increase your heat production, cost savings, economic benefits, financial return benefits by optimizing and increased efficiency of projects. I'd like to finish with the final slide, because we're all SPWLA members. Or if you're not an SPWLA member, I encourage you to go to the website and join. And as subsurface experts, we know the subsurface. So therefore, us as an industry, we've got knowledge to make geothermal energy technically and economically viable. On that, I'd like to give some acknowledgement. So, of course, Baker Hughes for allowing me to present the work. Of course, SPWA Columbia for inviting me. Very grateful for the invite. And NGSO for releasing the data I used in the case study. On that, I'll say thank you very much, and I'll be very happy to take some questions. And let me see. Oh, there we are. I found you again. I'd lost all the video.
Okay, Tom. Thanks a lot for this an excellent presentation. Really, really interesting. I think that this has been like very useful for opening the eyes to many people in the community. So we really, really appreciate. And now we are open for questions. Micah, do you see any question on the chat, or if you want to speak up and open your microphones, so more than welcome.
I apologize for
Yes.
having my camera turn off. I just didn't realize. So now you can see me again, if you want to, of course. Maybe not.
Yes,
but we'll leave
Ulysses.
that.
As a matter of fact, there are two of them in the chat. The first one said, is the double calc software available to anyone?
Yes, it is. In fact, let me see if the link is actually visible on the slide. So I've actually shared the slides. So I think Ulysses and Micah will be sharing this with you. So you want to read it, please feel free. But unfortunately, it's hidden at the bottom down there. But if you just do a search on Google, whatever, for double calc, you should be able to find it. Or the other link is this site here, nlog.nl. I'll type this in the chat actually. So
okay, yeah, that would be helpful.
There you go. So nlog.nl, and you go to that link. It'll probably come up in Dutch first, but if you look on, think the bottom, there's a link in English, and you go there, and you can actually go and download the software completely free.
Excellent news. The second question is there any water chemistry issues in the Dutch geothermal data?
Oh, yes. Yeah, as I sort of alluded to just in that earlier slide, is sort of geothermal industry here in Holland was started by farmers about 15 years ago. And everybody thought it was simple. You just drill a hole in the ground, find a porous permeable sandstone that's warm enough, and put it into the well, pump water around, it comes out hot, everybody's happy. Of course, then they completed these wells with steel casing. And let's think about it. Oil and gas well, what are we usually producing? Or what we hope we're producing? Oil and gas, hydrocarbons. They don't have any dissolved salt. They just don't corrode steel. Whereas here, we're producing subsurface water, usually quite saline, sort of several tens, if not hundreds of parts per million sodium chloride. Hot, salty water. What does that do to mild steel? It dissolves it. So they've got big corrosion problems with some of these early wells, and they're actually having to spend a lot of money on corrosion inhibitors just to prevent the casing basically dissolving. Another problem we've been having is, again, going back to the salty water, is when salty water cools down, what happens to the salt in this water? It precipitates. I've actually seen photos of tubing that's gone from diameter like this to this, because as the water gets cold, the salt comes out of solution and actually deposits in the tubing. Of course, tubing diameter reduces your flow. I mean, there's also examples of sort of adverse geochemical reactions. You haven't done any sort of water compatibility testing. Your injected fluids react with the formation mineralogy, water, whatever, and plug the pore throats, again, reducing flow. So the whole geochemical side can be a big thing to watch out for in these wells. The main one being the corrosions mentioned, but there's other things as well.
Very good. Excellent.
Well, here Manuel Rodriguez from Ecopetrol asks, what log suites are used for geothermal wells?
Good question. I think the best way to answer this is what log suites would be a good idea to take. Because again, going back to the early days, what was often found is many of the operators just thought, we just got to find a sandstone, and we'll use offset data to say these are known formations. Are they porous enough, permeable enough to produce? So quite often they just run a gamma ray. Just, okay, shale sand, shale sand, shale sand. Okay, we're in the sand we want. Let's stop now. Sometimes it also run a resistivity. Again, gives some idea. It's water filled. You've got a bit of porosity. Perfect. But nowadays, what I'm noticing is people starting to log more, or actually have the ideas of logging more. So the ideal things you need to measure: porosity and permeability. Again, flow is everything. So it's really porosity logs. So neutron density, of course, acoustics. I mean, neutron density, some operators are a bit reluctant to run it because we all know nuclear sources, the health and safety implications of running this if they get stuck, for example. So some operators are reluctant. Sourceless porosity is a good one. So I personally think that nuclear magnetic resonance logs are ideal for geothermal, because I'm sure many of you on the call are familiar with nuclear magnetic resonance. It's all seen as a slow log. It takes a long time to log it, mainly because of having to long T1s, long wait times to polarize the hydrocarbons. Of course, in geothermal wells, you've got no hydrocarbons, and water polarizes pretty quickly. And nuclear magnetic resonance will tell you pore size information. It'll tell you permeability information. You can infer things like grain size information, lots and lots of uses. So personally, I think NMR logs would be ideal for geothermal wells because they tell you so much. And also things, let's say hard rock prospects, fractured formations, image logs would be good. Really, it's any log we run in oil and gas to sort of tell us formation properties, especially porosity, permeability, are ideal. But again, going back to an earlier slide, because the economic returns on geothermal wells aren't as high as oil and gas wells, operators are often reluctant to run these because the costs at the moment are too high. And the question is, what can we do as an industry to make this more economic, either in terms of the value of the information, the return on the information, or standardization, best practices, commonality to reduce the cost of running these things? And
and I believe it's worth to mention that when it comes to data acquisition and electrical logging, we are dealing with hot environments. And we do face limitations as service providers when it comes to measuring in high temperatures.
This is another misconception, Ulysses, because you fall into the trap of thinking geothermal, it's steam coming out of the ground, which is only a very small part of it. Because I'll give the example here in the Netherlands and sort of district heating in general. We only need temperatures of about 80 degrees Celsius, not very hot. So standard technology is perfectly fine.
Okay. That's great.
Yeah. It's only when you get to sort of being obviously sort of things like Iceland, where you look at 250, 300 Celsius. Yes, it's getting hot. But I know a lot of the LWD providers have been looking at ways of cooling the mud while circulating. So even, yes, the actual static temperature is way above the ratings of the tools because you're circulating, cooling the mud. You're keeping the immediate environment below within spec, so you can still get the data. Yes,
there are several areas in Latin America, for instance, Mexico, where we are dealing with very high temperatures. The only way to log is just to cool down the wells, to cool down the mud system for either LWD logs or wireline logs. So,
Exactly. And something the industry is looking into, I know the whole service industry is looking into, how can we acquire this data sort of economically and just electronic sort of work and what we can do in terms of logging practice, acquisition practice to get this data in these hot wells.
Yeah, absolutely. Yeah.
Ulysses, I don't know if we have time for an additional question because we have one in the chat.
Yeah, absolutely. Yes.
Okay, Daria Jimenez said, asked what tracers are used for geothermal flow? Tracers.
The honest answer is I don't know. It's not something I personally looked into. So a good question, maybe something I should look into because, I mean, tracers are useful. Where's the flow going? Very useful thing to know, actually.
Okay.
So if anybody does have any more questions, obviously it's sort of evening for my time in the Netherlands, so I'm quite happy to hang around a bit longer and answer any questions anybody has. If anybody else wants to hang around.
I believe I have some additional comment or question for you, Tom. Would you have any comment on the assessment of rock properties, like the thermal conductivity, the specific heat capacity, and that we are not getting that from logs?
We're not actually, I mean, but the question is, I know sort of one thing that's been worked on extensively now in the industry is actually sort of the standard reservoir modeling software, putting all this into these models, because obviously geothermal prospect, you want to know how much heat is down there. Of course, then you've got sort of thermal capacity and of course conductivity, because I mentioned already, potentially geothermal is 100% renewable. But you, of course, are cooling down the formations when you're producing the water or circulating. So you need to have this heat to recover, what's that depend on your thermal conductivity and the rate of replenishment. Exactly. So again, yes, I mean, all these things are being looked at. And I know sort of within my company, we've got people looking at getting thermal capacity from logs. Many of the universities here in Europe, I mean, TU Delft being a very good example, are looking at exactly this, modeling thermal rock property, heat capacity in the formation from whatever subsurface data they've got, analogs, log data, so on and so forth. A lot of work being done on this because, of course, you want to know what your energy is going to be. You need to know how much energy is there in the first place and how much is going to come out.
Exactly. Yeah. Excellent. Okay. I believe that we are on time. In the audience, anybody else who wants to ask, take this opportunity for asking questions. If someone else wants to open the microphone, please go ahead. Otherwise, we're going to be closing the event today.
So I've just, if you want to see the presentation, I've shared it with the board, so they pass it on to you. And also, if any of you guys are SPE members, this is based on my SPE Distinguished Lecturer presentation from the last season. So you can actually log into the SPE Distinguished Lecturer site. And if you really want to watch it again, there's a recording of me presenting it there too. So the slides are available there as well.
Absolutely. Excellent. We really appreciate that. Okay, Tom, thank you so much for sharing your knowledge today. This has been really, really interesting for the community. I hope that everyone enjoyed. And now we can move to the last slide.
Okay. I say thank you for inviting me.
Absolutely, more than welcome.